have the pleasure of introducing Skuyler Herozog. He is, of course, a PhD student here at Mines, and he'll be defending his dissertation. Skuyler came to us from Washington State quite a few years ago, not quite a few, just a few. Came in luckily with a National Science Foundation graduate fellowship, and then we worked on a project. Skuyler wrote a proposal and that got funded, so for the most part, Skuyler's been essentially self-funded, which is unusual for a PhD student. The project he works on is pretty cool. It's evolved out of a sort of an idea we were talking about when I was on sabbatical at Stanford about looking at how natural stream beds might remove pollutants and recycled water. We get credit for that. But now it's evolved a lot into something new and interesting and something that most people think is very novel. There's a patent pending on it, so I think it's some really cool stuff, and I won't steal Skuyler's punchline. The last thing I'll say is that Skuyler's been a real leader here on campus in the student group. He was a leader in the Renew It program, although that wasn't really providing much of his funding except for the peripherals. And I think a lot of the students, maybe more importantly, a lot of the students in the department look up to Skuyler for advice and things like that. So anyhow, that's enough said. I'll turn it over to Skuyler. And I forgot to mention, Chris Higgins here is Skuyler's co-advisor. And actually, I'll let you introduce the rest of the committee. Okay.
Thank you, John. The rest of my committee, Kamini Singha is calling in here. We've got Junko is here, back here. Dr. Junko Munukanamar, Dr. Juan Lucena from Humanitarian Engineering, and these two advisors, thank you very much, John. Today I'm talking about biohydrochemical enhancements for stream water treatment, which is a mouthful, best for short, but in summary, we're looking at engineering stream beds to enhance the natural filtration capacity of the stream beds with the ultimate goal of improving water quality. All right. So I'll give a brief introduction here. The outline here, introduction and background. I'll go through the research questions and the hypotheses that I have. So in short here, we had a numerical model to test the proof of principle, as well as two flume studies. One for kind of hyper-exchange flow characterization, another one for the more relevant question of does this technology enhance water quality? I'll then go through conclusions, touch on the broader impacts and future work of this study. And you can see here on the bottom, there's a little progress bar to see where we're at with regard to this timeline. So I want to start with the bad news. The EPA did a survey of America's rivers and streams. The most recent survey found 47%, or almost half, of the nation's rivers and streams were degraded. The leading cause of this pollution is non-point source pollution, which is this kind of diffuse pollution, comes off of streets, farms, and fields. Because it's so diffuse, it's very difficult to identify and then treat. The leading cause currently is actually farm runoff, so a lot of nutrient pollution. But cities with rapid urbanization, cities' non-point source pollution is becoming most rapidly increasing category of non-point source pollution. And the top three contaminant classes of this pollution are pathogens, nutrients, and metals. Now, again, very bad news. There's a lot of different case studies I could tell you about to illustrate this, in addition to that broader nationwide survey. In Seattle, there's a lot of salmon dying before they spawn because of stormwater runoff. In the Gulf of Mexico and the Chesapeake Bay, there's eutrophication, algae blooms from too much fertilizer. But I want to do something close to home here. So this is Denver on the right-hand side of this panel. This is from the Department of Environmental Quality. And what you can see here is all the green dots are okay water quality. All the yellow dots are use caution, and the red dots are not safe for swimming and fishing. And so we have an issue here in Denver with E. coli from stormwater. The good news, that's the bad news, this is the good news. Streams are not just pipes. So they don't just receive the contamination from the city and the farms. They can actually actively process and treat that contamination. So I like to say the streams are not just recipients, but actually reactors for this pollution. You can see here, the good news with this also is that the streams integrate the entire upstream watershed. So all of that watershed area drains into one point in the stream. And because of that, we can take this non-point source diffuse pollution and basically treat it all in a centralized way in the stream bed. So I'm not at all advocating that we stop the decentralized treatment and prevention of contamination, but we should add in this element of in-stream treatment to mitigate some of that water quality impact. And one of the zones that's most effective as a reactor for contamination is actually this interface between the surface water and subsurface groundwater called the hypereik zone. So a bit more detail here. This is a very interesting dynamic area because you're at the interface of the groundwater and the surface water. So we have usually very well oxygenated aerobic water in the surface, anoxic water in the subsurface. You have slow velocities in the subsurface relative to the surface, and a lot of different microbes there. So summarizing a huge array of literature, the hyporheic zone, which is, I should say too, just a fancy word from the Greek for hyporeos, below the flow, can attenuate nutrients, metals, and pathogens. Again, those are the top 3 contaminant sources for water quality degradation in the US, as well as things that aren't regulated quite yet, so emerging organic contaminants and pharmaceuticals. So a bit more detail, how does the hyporheic zone actually remove these contaminants? There's a lot of diverse processes. Obviously, we need to have first flow through the subsurface before there's any treatment. If you bypass the filter, there's no filtration. But the second part that's more complicated is we need to make sure that the residence time of that water within the subsurface aligns with the reaction time scale. So I show here, you have basically well oxygenated aerobic water coming into the stream bed here because of this dune feature, and the short flow paths actually stay aerobic because there's not enough time to deplete the oxygen. Whereas some of these longer flow paths that come through here might actually turn anaerobic. This is very important because some of the reactions we want to target are aerobic and some are anaerobic. And so it's very important that we make sure if we are building something with a hyporheic zone, that we make sure that that aligns with the reaction of interest. So as a quick example here, nitrate is removed by denitrification, which is an anaerobic process. These short flow paths do not remove nitrate at all. It stays as nitrate. If we have a longer flow path, though, we can get denitrification, which takes this contaminant nitrate into a passive inert gas that's 80% of the atmosphere. So it's a very elegant process where we take something that's harmful and make it just fine. But again, those are the 2 key qualities. Number 1, exchange. Number 2, the right residence time for the reaction of interest. So how do we actually drive this hyporheic exchange? How do we get that exchange in the first place? The first 2 categories I'll talk about here, meanders and topography. So if you have this meander, the water on the upstream side of that meander is higher than the water downstream. It actually has a pressure gradient that will drive flow through that meander. And likewise with topography, if you have a shift, a pool and riffle sequence potentially, you can have hyporheic exchange as well. But those are obviously very difficult to change. We can change that with the river restoration project, but again, very time intensive, a lot of earthwork. And you can't always, sometimes we're constrained, I should say, by this field site, so we don't have room to make meanders. The next thing is bed forms. These are these little pools and riffles, ripples and dunes on the subsurface, on the interface there. Those can actually cause a lot of hyporheic exchange, but they're very difficult to maintain. As you might imagine, anytime there's a flood or anything like that, those are going to change quite a bit. So the default people use is typically these in-channel obstacles like this weir here. You might have seen things like this in streams in the area. Even Clear Creek has a bunch of these. And they do a variety of good things, including aeration and water quality, but they don't necessarily exchange the hyporheic water very well, and they don't control the residence times. So what we're looking at here is hydraulic connectivity instead. Spoiler alert, this is the focus of my presentation. And hydraulic connectivity is basically a fancy word for permeability. And it's somewhat counterintuitively abbreviated as K. There's no K in hydraulic connectivity, but remember this because it'll come up again and again. And I put a question mark here because some people wouldn't have said that this was actually a driver. They would say that yes, this can enhance exchange. If we have a more permeable bed, this weir will be more effective, but can it actually drive exchange by itself? We say yes, and I'll hope to convince you of that too. So in summary, we have a disconnect between all this hyporheic zone science I just summarized for you, and then the actual practice. So if someone wants to actually build a hyporheic zone restoration project utilizing some of these things, it's not very clear how to do that. So the worst case scenario is that urban streams also often have no hyporheic zone at all. This is in a concrete line channel here in Golden, absolutely no hyporheic zone or stream bed at all. So this is very good for flood control, but not so good for water quality. And what's more, there's no best management practice, which is another fancy word for basically structures or things that can enhance hyporheic exchange. There's no BMP that does both these 2 key categories. Number 1, driving exchange. Number 2, matching the residence times to the reactions of interest. No BMP can actually control the residence time at all. With that in mind, though, I want to convince you all that there are lots of opportunities to do this kind of invasive, very intense project. So the top left is a ditch here in Golden, Colorado. You can see they actually dug it all out, installed a liner, and then put in an aggregate of their own choosing. So they just bulk ordered some of the sand and put it in. So we could have done anything here with the same setup. Likewise, this is an erosion control project, which is very good for stream stabilization, preventing erosion, and maintaining some kinds of water quality. but not necessarily for treating some of the dissolved contaminants in water. Now, in the bottom case here, my advisor, Dr. Higgins, always makes me point out, it's not literally the same perspective, the same angle, but this is the same location. This is in Seattle. They bought this house, demolished it, and took this urbanized channel and made a nice floodplain project there. And on this project, they actually said, what's the best way to use the high break zone? But it wasn't very clear to them as practitioners how to harness the science that we have. So this is the topic of my presentation. As I've said, basically, the practitioners don't have a good BMP. And so here's kind of the BMPs that there are out there right now. These are all kind of the low head dam structures. There's J-hooks, there's crossfans. This crossfan is from Clear Creek and Golden. And the idea is that these can drive some localized exchange. There'll be some downwelling here and some upwelling here, but it's only very close to the structure. And these structures can only be placed about every 50 meters. And so you only have a very small impact from these structures on the reach scale. And likewise, there's no control about the residence time. And so you just kind of hope that the reaction that you get is the reaction that you want in this setting. So our motivation is to develop a new modular best management practice, basically one of these new structures that can do those two key things. Number one, increase hypertrophic exchange. Number two, provide customizable residence times that are site-specific, because some streams might have a copper issue, some might have an E. coli issue, some might have a nitrate issue. We want to be able to customize all of those modules to that site. So we were inspired, this is back to the permeability or K manipulations by a paper by Adam Ward, who basically showed with a computer model that by putting in these boxes of gravel or impermeable concrete or something like that, we can actually drive hypertrophic exchange. But in our opinion, it didn't go quite far enough because they only looked at one module and only a few of these orientations. And so we thought, can we do more with this? It's a very promising technology, but can we do more? So I want to go back to the base case here. The problem is that we have polluted stream water, and we do have this big hypertrophic zone filter potentially, but there's very much very little exchange. So most of this polluted water is bypassing the filter there. The flow through the stream bed might get clean, but never exchanges back to the surface, and so it's getting clean but not helping the water quality on the reach scale. So what we've done is called BEST, again, Biohydrochemical Enhancements for Stream Water Treatment, BEST for short, and there's three key features here. Number one is baffle walls, impermeable or locate blocks on the subsurface, and these actually force the water in and out of the hypertrophic zone. The second is geomedia, so we can add in activated carbon like is in a Brita filter or some other geomedia that can actually enhance the reaction rates within the stream bed. As I showed before in Golden, there's that ditch that was completely chosen from scratch. We could put in whatever we want at that channel to increase reactions. And then finally, by repeating these modules in series, we can get more and more percent or a fraction of flow from the stream through the modules, even though no individual module treats all the water. And also by positioning these in series, we can get controlled residence time because the second block makes the water downmost here come back up wherever we want it to be. Now, no one ever believes this actually works based on the conceptual diagram here, so I have a little flume experiment, including Zahi. I don't know if he's so this is the conceptual diagram. Again, we got the stream flow here going this way, and we have this hypertrophic zone here. And you can see the locate blocks that we installed, the impermeable walls. And here's a bit hard to see, but there's a little stream. Then we injected red dye in several locations into the stream bed. You can see that that water is carrying that red dye just in the same way the arrows are showing here. So I hope this convinces you that this actually does work. And I only show this now because it's a distraction if everyone's thinking, wait, does this actually work as I go on from here? So, all right, so I had 3 research questions. These are probably questions that you might come up with as well. Number one, before we put too much time and effort into this, can we use a computer model to simulate the exchange and the residence time to see if this actually is relevant? Does this work and is it relevant? Because even if it works, it may be such a small impact that it's not really worth doing. So we want to look at the relevance as well. Number two, if that works, can we go to a physical system and see if the exchange part of that piece actually does work? And number three, okay, even if there's exchange, does it actually remove contaminants of concern? Ultimately, this is our goal, to improve water quality. So I'll go into more detail on all these things, but that's a quick overview. So question one, again, can we simulate this? Does it actually work? Does it produce exchange and residence times? And our hypothesis, as you might imagine, is that yes, installing these locate blocks here will increase the exchange, constrain the residence times, and will lead to a better contaminant attenuation potential. Number 2, can BESS increase hypercritical exchange in a physical system? We hypothesized that yes, compared to an all-sand control, as well as some urban streams that were previously characterized in the literature, BESS will drive more exchange and have a better attenuation of this model compound or sazerain, which I'll go into more detail in the future. So we think, yes, this will work better. And then number 3, can BESS attenuate contaminants of concern? We think, again, yes, BESS will be able to attenuate ammonia, nitrate, and atrazine better than an all-sand control that's otherwise the same. So more detail on question 1 here. I want to emphasize this is a computer model, so not a physical system. But by using this numerical model, we were able to change a whole lot of different variables to look at different settings. And so we used groundwater vistas, which runs mod flow and mod path. What if we had a different slope? What if it's a very steep stream or a very shallow stream? What if we had a fine sand or a coarse sand? How would this change the flow through each cell, each module, and how would it change the residence time within that module? Then we could take those outputs from the model and run them with some literature data for reaction rates and see what that would produce in terms of water quality. I first want to emphasize that there is not necessarily one best module. We looked at a variety of orientations here. You can see A, B, and C and E down here actually have these impermeable blocks, whereas C and D just had high K or gravel. That is, that would pull more water in by being very permeable. And all of these did produce a hypercritical exchange. We found that A, B, and E were the best because these low K blocks actually keep that exchange going efficiently. Some of these other ones, there's water that's in the hypercritical zone already that stays in the hypercritical zone within and throughout the structure. So there's not as much efficiency of exchange. We also noted, we ended up choosing structure E because it was the best. It had the highest flow rate and a good residence time, but we also recognized that structure A wasn't that much worse, and it was much simpler because it doesn't have any gravel in it. So actually later on we'll use a structure more like this one. But for now we're focusing on structure E. And some more detail here, the BESS module is about 2 meters wide, 2 meters long, downstream with the treatment zone, and then we have a ½ meter on each side for these impermeable blocks. We're looking at a 1 meter wide, 1 meter deep hypercritical zone. And we said, okay, this in situ sand section here, what if this was a very fine sand, a medium sand, or a coarse sand? How would that change the outcome? So the results here, this is a bit of a tricky slide. I show the slope on the x-axis, and then this modular QBESS, which is the flow through each BESS module just for one. And what we see here, and then the fine and medium and coarse sand, there's a linear relationship between both the slope and the coarseness of the media, the permeability, which is exactly what we expect based on Darcy's law. But it's pretty cool to see. I said, okay, down below here, if we had 40 modules in series, which is an easier number to think about, 100 meters long reach of these BESS modules, how much flow would the system treat? So for a very coarse sand, it's about 10 liters per second, medium 1 liter per second, and very fine 0.1 liter per second. Obviously, 0.1 liters per second is not very good reward for a 100 meters long effort. So this may be too little to actually have an impact, which we'll see in a second. The other thing I want to point out, though, is that this is kind of based on the area. And so if we had a 2 meter wide stream instead of a 1 meter wide stream, we'd have double these flows. And likewise, if we had half, it would be half. So the other part of this that we care about is the residence time. And so here I show for the coarse sand, if we injected 5 different particles at the interface, how much time would those spend within the BESS module? I did 5 just for simplicity. You can see here a variety of residence times. We actually did this with 100, but it gets too kind of convoluted to show that all at once. But here's the cumulative distribution frequency diagram for those 100 particles. You can see here each of these little dots basically is a different particle. You can see different residence times. But if you don't like that, we just have the mean residence times here. So the coarse sand, again, that had the most flow through the system, but the shortest residence time, which makes sense too. Only 3.6 hours on average. Whereas the fine sand, by changing that media, we could get a residence time of 230 hours on average. And so this is a very important couple slides to show that the media has a tremendous impact on the flow rate as well as the residence time within the modules. So here's the impact of this. How much percent of contaminant can we remove from the stream itself? So we're looking at a 1 liter per second stream is the flow. We have this modular percent removal, so removal per module R. Basically, it's a function of this reaction term and the transport term. The reaction term is actually not as fancy as it looks. It's just simply, for each of these flow paths, let's do first order decay, and then average all the flow paths. You might ask, where we get this K for that reaction rate constant. I'll come back to that in a second. But then the other part is this Q best over Q stream. So how much water flows through the best module as a fraction of the water in the stream. This just basically scales it based on how much flow we're treating. So even if we treat 100% of the water in the module, if we only treat a little bit of water in the module, it's not a big impact on the reach scale. So back to these reaction rate constants. Crazy slide, don't worry too much about memorizing this, but we want to show for like nutrients and metals here, and then E. coli, if we had different geomedia, so again, activated carbon, or zero valent iron, or biochar, or wood chips, how would that change the reaction rate if we installed that media into that treatment zone? And what we find is there's a big impact, of course, on the geomedia. But first, I show here the results. This is the percent removal per module for the fine sand. And as you can see, it's not very much. This is because we're capped basically by there's such a low flow through the system that even though we remove all of that contaminant in each module, we're not just exposed to very much contaminant. In contrast with the medium, you can see this is rising a little bit because we have more flow and we still get good treatment. And finally, the coarse module has the most flow, and it still has a long enough residence time that we can get a lot of treatment in that cell. And so this one does the best for most reactions. So you can see here, most of these happen between 5 and 15% per module, which means that with 20 or less modules in series, we could get 100% removal of the contaminant in theory. I do want to point out a few things that are interesting here though. Number one, nitrate. Again, this one requires anaerobic conditions. So the short flow paths don't necessarily do very well for that removal. And so we actually see that the medium sand outperforms the coarse sand only for the nitrate because of that anaerobic requirement. Likewise over here, we have two different studies that both featured nickel removal with zero valent iron. And because those studies had very different reaction rates, the results are very different. So this highlights that we need to have very precise reaction rates and really understand the system we're working in specifically before we can design these modules appropriately. In summary of this section though, we looked at the hybridic zone and residence times and found they can be controlled by the media we put in as well as the module design. Likewise, the coarse sand, especially and potentially the medium sand, are relevant for attenuation of many contaminants in small streams. And we've put this, in theory, about 10 liters per second or less over a couple hundred meters reach length. And that's representative of many small streams in urban areas. And finally, again, the customization of these modules and the design of these modules needs very specific reaction rate constants and clear goals from the system. Because a lot of times we ask practitioners, what's the goal in the system? Do you want nitrate removal, ammonia removal, E. coli removal, or just habitat? And they say yes. So we need to know which of those specifically it is to be able to kind of optimize that system. So moving on to number 2 here, this is about the physical system. Shout out to my father-in-law that's cooler than me and has his own drone that allowed me to get a shot. So this is a mix of a physical flume system, which I'll go into detail on in a second, as well as some computer modeling to analyze those data. But you can see the system here at Mines Park on campus. So this stream system, we have 2 streams. One is an all sand control condition. The other one has best modules. And you can see here on the left-hand side the all sand control, and then the best modules here. And this is a kind of schematic of the cross-section. So you can see a few things different between the first study and this study. Number one, we have no gravel. We put in some wood chips there. We also had a 1 meter spacing instead of 2 meter spacing. And the hybridic zone is only 0.3 meters deep instead of 1 meter, and the same with the width. So it's a much smaller system, but the sand we use is the same as the coarse sand from Objective 1. So right away we can predict that this will have very fast flow, shorter residence times. So it's very difficult. The purpose of this study is to say, does this stream actually produce the exchange that we saw in the model? We want to prove this in an actual system. And so it's very difficult to actually measure the exchange and the flows in situ because it's in the subsurface, right? How are you going to measure the flow in the stream bed without disturbing the stream bed? So what we do often is use tracers instead. And so the conservative tracer here does not degrade at all. If we have a probe at the end of the stream reach and we inject the tracer in the start, we can see that tracer arriving downstream. And it doesn't get degraded, so we always see is how it moves with the water. So if that tracer is going down into the hybridic zone because of these best modules, it will get delayed. At the downstream end, we'll see this lag time where as it's rising, it will be slower, and as it's flushing at the end, it will be slower as well. Likewise, with the reactive tracer, this one actually does react. It's not conservative, and so if we have flow through the subsurface, we'll have both delay as well as reaction, so we won't get as much of it at the end as we injected. So this is very useful for this exact kind of study here. So again, at these flumes, we injected the tracers at the same time into the surface up here, then measured at the downstream end. And we used a model called stamped L, which I'll describe in a second, to look at the flow exchange and the residence times. And the idea is that we can actually calibrate this model with the salt tracer, and then if we did a good job with that model, we can actually produce the reactive tracer results that we saw as well. So that's our validation of the model. And then in addition to that, the reactive tracer we use, called risazorin, or RAS for short, is also a model contaminant. It degrades aerobically, so we can use it to also not only clarify what exchange is happening in the stream, but predict removal of other contaminants in this kind of system as well. So a bit more detail on RAS. Here, it's a blue fluorescent dye. It degrades in aerobic stream beds to resarufin, or RU for short. It's a very useful contaminant, our model contaminant for the study. And we had collaborators, Ricardo Gonzalez Pinzon at University of New Mexico, that analyzed these for us. So you'll see a lot of these data here. We're looking at the parent compound degrading into the daughter compound here. And a bit more on the model. The idea is that it's not actually a physics-based model that says what's the velocity here, what's the flow here, but rather we have a relatively mobile zone and a relatively immobile zone. And in the stream, this actually looks like the stream is mobile. In the hypergenic zone, although there is flow, it's much slower than the mobile zone, so it's relatively immobile. And the model works by saying, okay, how big effectively is this immobile zone? And then how fast does water exchange back and forth? So we can compare the effective sizes of the stream beds, basically, by doing this comparison. And I want to point out, technically this model measures something called hypergenic transient storage, which isn't worth really going into, but because our streams are very simplified, hypergenic transient storage in this case basically equates to hypergenic exchange. But I'll get into the results here. So the first thing we looked at with a tracer test, this is the conservative salt tracer. So if we did, just as an illustration here, a concrete channel that has no hypergenic zone, we expect very rapid rise to 100% concentration, and then as soon as we turn off the tracer, very rapid flushing back down to 0. So here's the data in the model for the control. And what you see here is this lag time rising, as well as the lag on the flushing, indicative of that delay within the hypergenic zone. So the control does have some hypergenic exchange in the system. And it's not surprising because it's actually, we use it as the control condition, but it's actually its own BMP, it's a sand filter. And so it's not surprising that it's doing pretty well for this exchange and treatment. Likewise here with the best, if we throw that in there, you can see there's a bit more lag on the rise and a bit more lag on the flushing too. This is a very subtle difference, but it is statistically significant. And it's only so small because we have a very short reach. That stream flume is only 12 meters long. And so if we did this on a more typical scale of about 100 or 200 meters, we would have seen a much bigger difference. But this is, again, significant. And what's really cool is the stamped L model tells us that the hypergenic zone in the best module is actually 50% larger effectively than the control. So even though we have the same exact dimensions, we're getting 50% more treatment volume by including these best modules. So here's the validation. So again, if we did well with this physical model, we should be able to match the reactive tracer model results as well. And so this slide's a bit complicated, I apologize, but it actually is much simpler than it was originally. So we injected at 1,000 nanograms per liter, or nanomolar, excuse me. And you can see that we actually have attenuated the peak by 15% in the control, and by, let me do the math here, 33% in the best modules. So we see a lower peak concentration in the best than the control. The other thing I want to emphasize to you here is that, again, in the conservative tracer model, we saw more lag in the best stream because we had that hypergenic exchange. So what you might expect at first is that the RAS observations here, we would see more lag in the RAS also. But in fact, we see the opposite. There's more lag in the control. There's basically no lag at all in the best modules. So you might ask yourself, why is that? Why don't we see this lag? And the answer is that any hypergenic exchange that causes that lag actually is removing the RAS. We would see it as RU instead. And so that's what we see here actually. We have a big tail, a big lag for the RU, but not for the RAS, which shows that there is that exchange and it's being reacted. This happened in both streams, but more so in the best, showing that we do get that exchange. We did a very good job matching the RAS data. We were underestimating the RU by a little bit, but we think that's because of we had slower reaction rates for RU degradation in our system than the control. Than the paper we use these rates from. But the important thing is to focus then on the data, and zooming in on some of these tails here, we got this really cool result where during the injection we see, this is, I should stop here for a second, sorry. So this is time on the x-axis and the concentration of RAS and RU in the best stream divided by the concentration in the control stream. So this is a ratio of the two streams. What we see is during the injection, they're about the same, about 1. But post-injection, we get this enrichment, especially in the best stream, of RU. So there's way more RU, the daughter products, in the best stream than the control. About 10 times as much, in fact. And so this is showing that we get much higher reaction rate again in that stream. So then we thought it'd be cool to extend these results and say, again, if RAS is a generic aerobically degrading contaminant, what can it tell us about the potential of best modules to treat other things? So again, we start with this the concrete line channel as a base case. And because there's no hypergate exchange, again, there's no degradation. So if we look at longer distances with this calibrated model, up to 300 meters of reach length, we see basically no removal of RAS by the concrete channel. Now with the control and the best, we see some removal. Both do actually quite well, but the best does 50% better than the control. And so it would take the best 125 meters of reach length to get 1 log removal of RAS. It would take 50% longer, 190 meters, for the control to do the same exact distance. And what's really cool is we had there was a paper previously published that did this kind of same analysis with the stamped L model. So we got these streams from Jackson, Wyoming, that are in the Rocky Mountains also, and could plot how they would do in comparison. And like we would expect, they're somewhere in between this concrete line channel and the control, because they're not concrete line, they do have some stream bed, but they're also not a BMP, they're not a sand filter. And so the implications of this study is that we can outperform the sand filter by quite a bit by installing these BEST modules, or potentially if we did a stream restoration on these streams, we could shift those lines further down and get better removal of other aerobically degrading contaminants like PAHs, ammonia, some other things in these streams potentially. So summary of this section here, the BEST increased the hypergate exchange treatment volume by 50%, as well as the risazorin removal by 50%. But it's even better if you compare to the the concrete line channel, or these actual urban streams, because the control itself is a BMP again. And so we were able to show that the BEST has much better exchange than previously found in other streams. So the third question here is the one that most of you probably care about, maybe the only one you care about. When I go to conferences, people say, those first 2 experiments are great, very interesting, but how does this apply to the real world? We want to see actual data here. And so that's what we did in the third study. We said, what if we dosed these flumes with ammonia, nitrate, and atrazine? Ammonia and nitrate are both fertilizers, nutrients that can cause either acute toxicity or algae blooms. Atrazine is a herbicide that causes a variety of issues, including change of gender in frogs. So these are real contaminants that we can look at. And because they're less reactive than RAS, we have to do a recirculation experiment. So we just recirculated those flumes over 6 hours to simulate a longer reach length. All right, so we had 3 conditions. We had a high ammonia, I should go back real fast. We had a high ammonia, low nitrate, and high nitrate, low ammonia condition for the nutrients. This is important because ammonia actually degrades into nitrate in aerobic conditions. And so we can actually produce nitrate if we remove the ammonia. But the goal is eventually to get this into gas, which again is 80% of the atmosphere and causing no problems to anybody. So this is a simplified reaction progress here, but this is the goal of the system. So we looked at those 2 conditions, and then we also added atrazine and looked at the 2 daughter products or metabolites here, DEA and DIA. So the first result here, I'm focusing on ammonia removal. And at first glance, we thought this is actually a little bit disappointing because the BEST did great, removed 99% of the ammonia in 6 hours, but the control also did pretty well, about 90% removal. So at first we were saying, it's great that both did well, but how much better was the BEST for all the effort? But then we looked at this in a log scale and realized actually the BEST did about twice as well. So now this is not percent removal, but final concentration is a fraction of the initial concentration. You can see that if we plot this in log scale, the BEST did much, much better. So this, the effective reach scale reaction rate is actually 95% faster than the control. So we're seeing a big benefit from the BEST. Putting this in real world context, if you had the same exact flume stretched out we predict conservatively that it would take 1.2 kilometers for the best to treat that ammonia to 1 log removal. We take almost double that distance, 2.2 kilometers, for the control to do the same thing. So this is a really cool result. And I want to emphasize that's still pretty long. It's longer than we wanted. But remember that these are very small flumes, and if we increase the width, we can get more treatment. And so if we went from 0.3 meters wide to 1 meter wide, we would triple that, or actually divide by 3 that distance. And so just by doing that, we can get to about 345 meters, again, as a conservative estimate for the best, 690 meters for the control. And so these are getting towards the reach lengths that we're looking for. We can also increase the hybridic depth more, again, 0.3 meters versus 1 meter from the first study, although that doesn't scale quite as linearly as the width does. Now we had a bit more trouble with nitrate, which again is not unexpected given that we have these coarse modules that have very high flow rate and not much residence time. So we saw slightly better attenuation of nitrate in the best and the control, about 40% versus about 34%, but this was not statistically significant. So this was a bit of an issue, but again, we realized this is an aerobic module, very fast flow rate, and so this is not necessarily bad news. It just shows that we need to have a different module to target nitrate removal, which is something we're going to look at with future work. I'll talk about that later on. The other thing we saw, as I alluded to before, this is a plot of the 2 streams for ammonia here in these curves and the nitrate in this curve. You can see that as we remove ammonia, that reaction is happening faster than the denitrification reaction. So we actually have this buildup of nitrate over that 6 hours. So this is very important to realize, again, the limitations of the system. Potentially, if we have too much ammonia, we can actually cause rising nitrate. Eventually that would be removed, but in the meantime, we need to be conscious of maybe creating another problem as we solve a different one. So in summary, kind of this area here, these slides, this oxic aerobic best, which we did show also with DO measurements. We took DO measurements in the best modules and saw that there is a lot of DO still. They're not best for denitrification, but they are very good for ammonia removal. Really cool results for atrazine as well here. So you can see basically no removal at all for the control, and about 44%, I think, removal for the best, 42% there. And this was, of course, statistically significant. And what was interesting, we found no metabolites of atrazine. So it wasn't degrading, we don't think. What we think happened is that we included the wood chips in the best module. And because of the added flow through the best stream as well as those wood chips, we actually had a higher absorption of those contaminants to the wood chips. And a simple kind of equilibrium partitioning analysis supports this. We estimate that based on the wood chips, the lack of wood chips in the control, the concentration that we predict is about what we saw. With the best, the concentration we predict is a little bit lower than what we saw, but it makes sense that there might be some kinetic limitations. It might take some time for that reaction to happen, that absorption to happen, that would delay that. So it makes sense to what we see here. Basically, in summary, we think the wood chips totally explain the difference here. So it highlights the importance of having the right geomedia in the modules to target reactions of interest. So in summary for this section, best significantly increased the removal of ammonia and atrazine compared to the control, but not for nitrate. So we need a different module designed for nitrate. Similarly, the nitrate behavior is a source sink, which is well documented in the literature. That sometimes we remove nitrate, sometimes we add nitrate based on the conditions. We see that a lot in the literature. And that and the atrazine absorption highlight the need to really tailor the module, again, with the right redox conditions and the right geomedia for the reaction of interest. So I personally don't feel that these results show negatively on best for nitrate removal. They simply show we need a different module that's better optimized for that reaction. So conclusions overall here. Best is a unique BMP. We can do those 2 things that we really want to do: drive hybridic exchange and control residence times based on the spacing of the modules as well as the media we put in there. Conclusion number 2, best increase the hybridic zone treatment volume effectively, as well as the rosazine removal by 50% compared to the all-sand control, and did even better compared to the urban channel.